We're going to work towards setting up applications of integrations, first by talking about finding areas between curves, which is exactly our question. How do we find the area between two curves? And we'll start out by kind of mapping out the idea behind what we are doing. If I've got some graph, let's say there's some function f of x going from a to b. And beneath it, there's some other function. We'll call it g of x between a and b. What we're trying to do is find the area between those two curves. Now, if I were to just integrate from a to b of f of x dx, that would give me the entire area down to the x-axis. But we don't want that. In fact, what we don't want is the g of x part, the underneath part. We want to get rid of that part. So what we'll do is we'll subtract the integral from a to b of the g of x dx. And when we do that, it will give us, in red here, the area in between f of x and g of x. Now we can clean that up a little bit and bring that together. Because we're integrating from a to b on both of them, we could just write that as a single integral of f of x minus g of x dx. In other words, we find the area underneath the top curve and subtract the area underneath the bottom curve. I should have numbered that number 1. For number 2 here, though, just to give a little bit of a special case here, let's say my f of x is decreasing and my g of x is increasing. But we still want the area from a to b. We still want the area between these two curves. What happens here, though, is they cross. The two curves cross at some middle point. I'll call that middle point C. And what happens is now the top function is the bottom function, and the bottom function is the top function. And we have to account for that in our integration. So first, we'll integrate just from a to c, where they intersect. And we'll take the top function f of x and subtract the bottom function g of x dx. Then we'll add to it the right side. But on the right side, as we go from c to b, you'll notice the g of x function's on top. So we'll start with g of x and then subtract off the bottom function f of x dx. And so sometimes what we have to do really is we divide the graph into two parts and find the area of the left part separate from the area of the right part, and then add them together. So that way the top function is always positive and the bottom function is always negative. So that's kind of in theory what we're doing. Let's work out some examples so we can get good at finding the area between two curves. Let's start with a simple one. We're going to find the area between f of x equals x plus 5 and g of x equals 2x plus 1. And we're only going to be interested in the values between 0 and 4. So x plus 5, that's this first function, x plus 5. And then the 2x plus 1's got a lower y-intercept, but it's steeper. And we're interested in going from 0 to 4. Now, I want to know, do they actually intersect at 4? One thing we can do to figure out where these intersect is we'll set the x plus 5 equal to the other function, 2x plus 1. And sure enough, if we subtract x and subtract 1, we find out x equals 4 is where they intersect. So we really are finding the area of this triangle between our two graphs. Let's move the x plus 5 on top. The blue graph, x plus 5 is on top. So to do that, we will take an integral. We're integrating as x goes from 0 to 4. And we'll take the top function, which is the x plus 5, and we'll subtract the bottom function. As we subtract, it's going to change the sign in front of each term. So we'll have negative 2x and negative 1 dx. Combine like terms on this before we solve. From 0 to 4 of negative x plus 4 dx. And now we're ready to actually integrate. When we integrate it, we get negative x squared divided by 2 plus 4x integrated from 0 to 4. So first plugging the 4 in. Negative 4 squared is negative 16 over 2 plus 4 times 4. And then we would subtract plugging 0 in. But if we plug 0 in, 0 squared over 2 plus 0 times 4 is just 0. So that's kind of nice. It's all 0. So what we end up with is negative 8 plus 16, or just an area of 8 square units between x plus 5 and 2x plus 1. Now that one's probably a little simple because those were all straight lines. Let's do one a little more interesting. Let's find the area between f of x equals x squared minus 4 and g of x equals x plus 2. Now, if you remember your properties of graphs, x squared minus 4 we'll know is a parabola that comes down 4 units. That's the f of x. And for the g of x, x plus 2, that's going to have a y-intercept of 2, and it's going to have a slope of 1. And so it's going to look something like this. We're being asked to find the area between the two curves. How much area is there in that space? Now, if you forget exactly how the graphs look, or if some of the graphs are more complex, don't hesitate to use your graphing calculator to help you graph the different functions. Or I also highly recommend the online graphing calculator or the app on your phone, Desmos. They're really good for graphing and zooming in on certain areas of the graph, so you can see exactly what you're taking the area of. Now we can see our x values are going to range down to this bottom point off to the left, and then x is going to grow up to this top point off to the right. But we don't know exactly what x values those are yet. The way we can find them is we will set the functions equal to each other to see when they cross. X squared minus 4 equals x plus 2. Subtracting x gives us x squared minus x. Subtracting 2 gives us minus 6. Factoring to x minus 3, x plus 2. So we can see that x is equal to a positive 3 and a negative 2. So the one to the left must be negative 2, and the one to the right is when x equals 3. So that tells us we're integrating from x starting at negative 2. It's going to move off to the right all the way up to 3. To find our area, we just subtract the functions. Notice the green function, the g of x is on top, so that's our positive x plus 2. The blue function, the x squared minus 4, is on the bottom. That's what we're going to subtract, which changes the sign. Negative x squared plus 4 dx. And so if we combine like terms, we're going from negative 2 to 3 of negative x squared plus x plus 6 dx. Now that we have the function, it should integrate really nicely. we end up with negative x cubed divided by 3 plus x squared divided by 2 plus 6x integrated from negative 2 to 3. All right, let's plug in those limits of integration. We have negative x cubed. Negative 3 cubed is 27 thirds. Plus 3 squared is 9 halves. Plus 6 times 3 is 18. Then we subtract off the lower limit. When we plug negative 2 in, negative 2 cubed is negative 8. The opposite of negative 8 is positive 8, but we subtract it off, so we have negative 8 thirds. Negative 2 squared is 4. Divided by 2 is 2. Subtract 2. And negative 2 times 6 is negative 12. Opposite of that's a positive 12. And so when we plug all that in our calculator, negative 27 thirds plus 9 halves plus 18 minus 8 thirds minus 2 plus 12, change it to a fraction, we end up with 125 sixths is the area between these two curves. Let's try another example that's a little more interesting. Let's find the area between f of x equals the square root of x, g of x equals 3 halves minus x over 2, and h of x equals 0. So f of x equals the square root of x is going to be this blue function. G of x starts at 3 halves and has a slope of negative 1/2, so it's this green function. And h of x is 0. That's just the x-intercept, so we don't need to really draw it. The x-intercept is kind of our bottom limit. We're finding our area of this shape. What's nice about these shapes is the bottom half is not another function. The bottom half is just 0, so we don't really have to subtract anything off. But what you notice is we really have two different parts to the function. The left part of the function, that I'll highlight in yellow here, is under the square root of x. The right part of the function, that I'll highlight in pink, is under that linear equation, 3 halves minus x over 2. So we're going to need a separate integral for both halves. First, we'll take the integral. Actually, we need to know a couple things. We need to know where the graph starts, where they intersect, and where we hit the ground. Where the graph starts on the left, that's where the square root of x hits the x-axis of 0. And if you square both sides, we see x is equal to 0 at that point. On the right side, that's where the green line hits 0. So we could say 3 halves minus x over 2 equals 0. Multiply everything by 2 gives us 3 minus x equals 0. Add x to both sides, and we get x equals 3. So we've got an x-coordinate of 3 on the right. In the middle, this is going to take a little bit more work. We want to know where the green and the blue line intersect. So we'll set them equal to each other. 3 halves minus x over 2 equals the square root of x. Let's get rid of the fractions by multiplying by 2. Gives us 2 square roots of x. Square both sides gives us 9 minus 6x plus x squared equals 4x. Subtract the 4x from both sides, putting it in order. X squared minus 10x plus 9 equals 0. Factoring. X minus 9, x minus 1 equals 0. So x is either equal to 9 or 1. Well, we know we have to be less than 3 because we've got that point of 3 on the right, so it must be the 1. If I wasn't sure, though, we could plug them back into the original equation, and we'd find out that that 9 is an extraneous root. So 1 must be our solution. All right, now we have everything we need to know. Now we're ready to set up our integrals. First, we're going to integrate from 0 to 1. This is that yellow part. And notice the blue line is on top. That's the f of x function, the square root of x, or x to the 1/2 dx. And I'll put a yellow line over it so we know that's the yellow part. But in addition to that, we've got the right part, which is the green line. So we're integrating now as x goes from 1 to 3 of the green line, which is 3/2 minus x over 2 dx. I should probably write that in green because that's the green function. 3/2 minus x over 2. And I'll put a pink line over that to say that represents the pink part of that shape. And now we're ready to start solving. X to the 1/2, that becomes x to the 3/2 times 2/3, integrated from 0 to 1. Plus, we have 3/2 x minus x squared over 4, and that's integrated from 1 to 3. I'm going to scroll down a bit to give me some space, because this is going to be a little bit longer. So first, plugging 1 in to x to the 3/2 gives us just 2/3. Minus, plugging 0 in gives us 0. Plus, plugging 3 in, 3 times 3 is 9/2. Minus 3 squared is 9/4. And then we'll subtract, plugging the 1 in, which gives us minus 3/2 plus 1/4. And so we have 2/3 minus 0 plus 9/2 minus 9/4 minus 3/2 plus 1/4. Plugging that into our calculator, we get a total area of 5/3. Let's try another one that we have to partition, but for slightly different reasons. Let's find the area between f of x equals x cubed plus 3x and g of x equals 4x. I would use a graphing calculator on this or use Desmos. And the scale's not too important in our picture as long as we get an idea of what's happening. The cubic you'll see comes up. Actually, let's do that in blue. The cubic you'll see comes up, levels off, and then goes back up. The linear function g of x comes in diagonally, hits the x-axis, and comes out diagonally. And so the area between the curves, there's two parts, a part on the left and a part on the right. We're going to need a different integral for each part. So first, maybe if I highlight in yellow the first part and in pink the second part, because there's a different function on top for each one. That's going to change our limits of integration. We also need to know the intersection points. We have a pretty good idea that the first intersection point is 0, but for the other ones, we'll need to set the functions equal to each other. X cubed plus 3x equals 4x. Subtract 4x, we get x cubed minus x equals 0. Factor out an x, leaves behind x squared minus 1. Factor the difference of squares, we have x plus 1, x minus 1. And so we know our values are 0, as expected, -1, and +1. So x is -1 on the left, positive 1 on the right. We now know what limits we have to take of our integration as x increases from left to right. We're going to integrate from -1 to 0. This time, the blue function's on top, the cubic. So we'll start with that, x cubed plus 3x. And we'll subtract the lower function, the minus 4x dx. That will give us the yellow piece. Then we'll add to it the integral as x goes from 0 to 1. But now the green function's on top. So we'll start with the 4x, and we'll subtract off the x cubed plus 3x. Oops, x cubed minus 3x, because we're subtracting the whole function, dx. And that will tell us the pink piece. Then we're ready to actually evaluate those integrals. We know that's going to be x to the 4th divided by 4 plus 3x squared divided by 2 minus 4x squared divided by 2. Actually, 4 divided by 2 is 2. So I'm just going to say 2x squared. That's being integrated from -1 to 0. Plus the second half, we get x squared divided by 2, which makes it 2x squared, minus x to the 4th divided by 4, minus 3x squared divided by 2. And that's integrated from 0 to 1. So on this first part, if we plug 0 in, nothing exciting happens. Then we're going to subtract the -1 plugged in. So we have -1 to the 4th power is 1. But we're subtracting, so 1/4. -1 squared is 1 times 3 halves, but we're subtracting the 3 halves. -1 squared is 1 times -2, but we're subtracting, so it's going to become a positive 2. On the right side, we're plugging in, starting with the positive 1. So if we plug in positive 1, we get plus 2 minus 1/4 minus 3 halves. Oops, that should have been 3 halves on the left side. And then when I plug 0 in, everything goes to 0, so there's nothing exciting left. And so what we have is -1/4 minus 3 halves plus 2 minus 1/4 minus 3 halves. Use the fraction button on the calculator, and we find out that that area is 1/2. And so that's how we can split up the functions to find the areas of the individual pieces. When the top function switches with the bottom function, we need to set up another integral. But there's actually another way to solve this problem that would have saved us quite a lot of grief. Let's take a look at that. Number 5. Sometimes we can use symmetry to our advantage. So we're doing the same functions, f of x equals x cubed plus 3x, and g of x equals 4x. And trying to draw that same graph here, the cubic came up, leveled off, and took off. The linear function came down, hit 0, and continued out. And what you notice, if I had drawn this to scale, if you graph it on Desmos or on your calculator, you'll see it a little clearer, is the left and right side are exactly the same shape and exactly the same size. Because they're exactly the same shape and same size, we only really need to find the area of one of the pieces. And then we'll double that area to account for the other piece. So I'm just going to do the integral from 0 to 1 of that right side. The integral from 0 to 1, and then we'll multiply the result by 2. So 2 times the integral, with the green on top, would be 4x. Let's do that in green. Minus the bottom function, minus x cubed minus 3x dx. that becomes 2, let's do this in purple, times 2x squared minus x to the 4th divided by 4 minus 3x squared divided by 2 integrated from 0 to 1. So we have 2 times, plugging 1 in is really nice. We're just left with 2 minus 1/4 minus 3/2. And when we plug 0 in, everything goes to 0. And now I can plug this in my calculator, multiplying by 2 out front, and we end up with the same answer of 1/2. And that symmetry made solving the problem a lot easier. So always be aware of looking for symmetry as you solve these problems. Symmetry can simplify the amount of integration we actually have to set up and evaluate. There is a slight twist we can do to this assignment that we're looking at today, and that is instead of just integrating as x moves from left to right, sometimes it's easier to integrate with respect to y. And the idea here, setting this up, is really similar. We're going to have some function, maybe it's g of y. And we'll have another function, maybe it's f of y. And we're interested in the area between them from a to b. But this time, a and b are y values. It's still the exact same idea. We're still integrating from a to b. And we still take the top function. You notice the f of y is higher. We're looking at it sideways. The f of y is on top of the g of y function. And then we'll subtract off the g of y function. And we'll take that integral with respect to y this time. And that can give us the exact same area. But sometimes doing it with y's is much easier than doing it with x's. And the great example of that is the example that we did up above. I think we called it example 3 previously. When we found the area between f of x equals the square root of x, g of x equals 3/2 minus x over 2, and h of x equals 0. If you remember when we graphed that, we had our square root of x. We had our 3/2 minus x over 2, and then h of x at 0. And that gave us this. It's kind of like a triangle with one side's kind of curvy. And we wanted to find the area of that. We had to do it with 2 different integrals when we were integrating with respect to x, because there was a change in which function was on top. But if we integrate with respect to y, first we'll change all these functions to y functions. So y equals the square root of x. If I square both sides, we get y squared equals x. That's my new blue function. With the g of x function, y equals 3/2 minus x over 2. If I multiply both sides by 2, we have 2y equals 3 minus x. Add x and subtract 2y. We have a new green function. So the green function we can now think of as 3 minus 2y. The blue function we can think of as y squared. We still need to figure out where they intersect. We know they intersect when x is equal to 3. I'm sorry, when x is equal to 1. But we don't know what y equals necessarily yet. So let's set them equal to each other. Y squared equals 3 minus 2y. We'll add the 2y. We'll subtract the 3. We'll factor to y minus 3. I'm sorry, y plus 3. y minus 1. So y is negative 3 or positive 1. Well, if we had gone off with our y squared, we would have ended up with that negative 3 value down there. But we're interested, for our purposes, in just that 1. The y's are going from 0 up to 1. That's what we want to integrate. We're going to integrate the y's from 0 to 1. And if we look at it sideways, we see the green function's on top. That's the 3 minus 2y. And then we'll subtract off the blue function, the y squared. And we'll integrate that with respect to y. And now, rather than having 2 integrals like we did before, we only have 1 integral. Hopefully, we get the exact same answer. Let's see. Taking the integral, we have 3y minus 2y squared divided by 2. The 2's divide out. Minus y cubed divided by 3. Integrating from 0 to 1. If I plug 1 in, we get 3 minus 1 minus 1/3. And then we would subtract, plugging the 0 in. But what's nice is all that goes to 0. And we end up with the exact same answer of 5/3. And so sometimes we're going to find it's easier to integrate with respect to y. Sometimes it's easier to integrate with respect to x. But the idea is exactly the same. If we want to find the area between two curves, all we need to do is take the integral and subtract the two functions. So take a look at trying some of these on the assignment. Come to class with any questions that you might have. And we will see you then to talk about these in more detail.